This is chapter 7 that we are starting here, and this chapter is all about the atmosphere, something that's very important for both you and me because it's what we breathe. So we kind of need to know a little bit about it. This first little section here, just an intro to it. Some of these things we will be talking about later on in this section or in this later on in the chapter. The atmosphere, by definition, is the blanket of gases that surrounds our planet. Now, we stay pretty low in our atmosphere. This blanket of gases extends for many, many, many miles away, hundreds of miles away from the Earth's surface. Right here at the Earth's surface, though, it does contain just the right mix of oxygen, nitrogen, carbon dioxide, and other gases. It does shield the Earth from harmful radiation. We'll talk about both of those a little bit later on in this section. Helps regulate the temperatures on the planet's surface. All these mix of gases, it does affect our temperature. It also helps distribute water. That's not something that we often think about. However, that is true. The water can go anywhere in the world as a result of traveling through the atmosphere. Some places have more water in the atmosphere for a time. Some places have less. So that does play a factor, especially in weather patterns and temperature. The atmospheric composition. If we look at the atmosphere by composition, it really divides up into two groups. There's the lower atmosphere and the upper atmosphere. The lower atmosphere is from the Earth's surface to an altitude of around 50 miles. It has a fairly constant chemical composition. We also call it the homosphere because of this constant chemical composition. Because homosphere means same sphere, same realm here. It's another name for the lower atmosphere. And exactly what the lower atmosphere is composed of is 78% nitrogen. This is the most abundant gas we breathe, and it does absolutely nothing for us as living beings. Now, its presence does do a lot for the world in general, but as far as our bodies are concerned, we do not use this atmospheric nitrogen. It's the wrong kind of nitrogen. Our bodies does use nitrogen from certain foods we eat, but not from what we breathe in. Now, what we do use from the air we breathe in is this 21% oxygen. This really is a very good mix. Some of you may also remember that oxygen is necessary for starting fires. If this oxygen percentage were much higher, fires would not be controllable. And pretty much everything would burn up the first time a lightning storm happened. So yeah, this 21% oxygen seems fairly low for something that's so important. However, it is enough. Then there's 1% argon, and then 0.003% carbon dioxide. Now, keep in mind, all of these percentages are rounded off. These are not specific, because if you're doing the math, that's over 100%. So this 0.003% carbon dioxide, even though it's a small percentage, it is plenty of carbon dioxide to support all the plant life on this Earth. And it's a nice dichotomy here. We use the oxygen, give off carbon dioxide. Plants use the carbon dioxide, give off oxygen. Years ago, there were studies done, and in a carbon dioxide-rich environment, so slightly more, plants grow pretty well. Actually, they grow better than they do with less carbon dioxide because they utilize that. They don't use oxygen. Oxygen is a byproduct. The other thing that's in the air here, well, there's a few other things. One of the more important ones is water vapor. Now, that varies from place to place and from time to time. In the Pacific Northwest, depending on where you are, some places have almost no humidity, and it's rather nice that way. Other places can get high humidity, especially if you're living closer to the ocean. Puget Sound area can have a higher humidity from time to time. Depends on temperature, depends on location, depends on altitude. So all those factors do affect humidity. I went to college in Florida. Florida has a very high humidity, high temperature, low altitude, right next to the ocean. I lived in Pensacola. So all that combined to give a lot of humidity. I've also been in Missouri during the summertime. It is close enough to the Great Lakes region that the water there can inspire the humidity to go up. Now, also the upper limits of the homosphere contain ozone. This is an important compound. We'll talk about it a little bit later. And then there are traces of other rare gases. They're so small that they don't really do anything to us. So that is the composition of our air. And we kind of already mentioned some of these important ingredients here. Oxygen is vital to humans and animals. Carbon dioxide is vital for plants. Carbon dioxide and water combine to work, giving the Earth a mild, stable climate, meaning that it's a climate that we can live in. There are some extremes as far as cold and hot, especially in the deserts. We can see some of those extremes. One of the reasons why is because there is very little to no humidity in the desert. So it doesn't hold heat, it doesn't keep it from gradually changing. So it can go from extremes of below freezing at night to scorching during the day in the deserts. The ozone helps protect the Earth's surface from the sun's intense ultraviolet radiation, which we'll look at in just a little bit here, exactly how it does that. The distinctive layers here, more than 50 miles above the Earth's surface, is the heterosphere, roughly 85 kilometers up. You see it in the diagram there. And that just simply means different sphere because it is characterized by several layers of different gases, forming those distinctive layers that the title mentions. The turbopause, which we'll explain that particular title for that in a few minutes, the boundary or transitional zone between the lower and upper atmospheres. That marks the difference on the picture. It's this red ring there. And the gases in the middle and upper regions of the heterosphere are so thin that for practical purposes, they can be considered space. Almost all space missions have actually happened, well, I should say almost all. The vast majority of them have happened within our atmosphere. Obviously the ones going to the moon or further, such as the Voyager space probes and stuff, do not take place in our atmosphere, but a lot of the, like the International Space Station and many other missions, are actually within our atmosphere. Now, that being said, the atmosphere is so thin, it acts like empty space. And so we actually have to treat it that way. There's not enough pressure, there's not enough oxygen, it's extremely cold, all that kind of stuff. So a different way of looking at the atmosphere. We had the homosphere and the heterosphere. And now if we look at it as far as especially looking at temperature, the way the temperature acts going higher in our atmosphere, we could group them differently. We have the troposphere here on the surface. This is to an altitude of about 7 or 8 miles. This is also called the weather layer because this is the layer, the troposphere, is the layer where all the weather takes place. Above that, there is no drastic change in weather. This is where storm clouds happen, everything happens. Lots of planes do like to fly above it. Why? Because it makes it an easier flight. They can see further, there's nothing getting in the way, that kind of thing. This area, these layers are marked by a temperature gradient. A temperature gradient is just a steady change in temperature as altitude increases. On the troposphere, we go from warm to cold. The higher we get, the colder it gets. At the top of the troposphere is the tropopause. It is the boundary at the upper end of the troposphere, has a steady temp of around negative 76 degrees Fahrenheit. Now notice this pattern. Troposphere, boundary, tropopause. We have to pause before we go to the next sphere, which is the stratosphere. It is immediately above the tropopause. It is characterized by strong, steady winds, little changes or few changes in weather. The temperature gradient is opposite that of the troposphere. In the troposphere, we went from warm to cold. In the stratosphere, we go from cold to warm, and it is marked by an upper boundary called the stratopause. And in the stratosphere area there, we have this ozone layer. Now, we mentioned that this protects us from ultraviolet radiation. There are actually 3 forms of UV radiation: UVA, UVB, and UVC. UVA is the least harmful to us. It is practically unaffected by the ozone. You can see in the diagram it says like 5% of it is absorbed. Practically nothing, really. And then we have UVB. This is the mid-range. This really is what causes tannings and burnings. It is mostly absorbed by the ozone. Our diagram there says 95%, roughly. So some of it does get through. UVC is the most dangerous if you were to be exposed to it. However, the ozone layer protects us from all of UVC. It reacts to the ozone layer. Now, you may have heard of the hole in the ozone. That is an exaggeration. What it is that over the Antarctic area, there is an area of the ozone layer that thins for part of the year. It gets down to about half the thickness that it normally does. It used to be thought that this was caused by man-made reasons. After study, they found out that it was not. It was years of study. laws were passed based off of false, or what turns out to be false information, and many of those laws are probably still in effect today. But yeah, people got on the bandwagon, they knew a little bit about something, and before the research could actually be completed, actions were taken, people made decisions based off of incomplete information. And we now know that the thinning of the ozone layer is a seasonal thing. It actually thickens up each year also, and that it is not man-caused at all. Above the stratosphere, we have the stratopause, we have the mesosphere. This is immediately above the stratopause, and then we're flipping back around from warm to cold again. Temperature drops to a chilly negative 150 degrees Fahrenheit. It is bounded by the mesopause. See that pattern? Mesosphere, mesopause. This is the coldest point in the atmosphere. Boundary between mesosphere and thermosphere. Also the boundary between the homosphere and heterosphere. Actually, that should be the thermopause. We have a typo there. Sorry. The thermosphere is temperature can exceed 3,000 degrees Fahrenheit, 53 miles to 300 miles above the surface. And the thermopause is that boundary between the mesosphere and, it's between the thermosphere and the exosphere. And it's also the boundary between, hang on. Nope, I do have it up there right. Mesopause is the boundary between the homosphere and the heterosphere. I kind of got ahead of myself and looked at things weirdly. Thermopause is the boundary between the thermosphere and the exosphere. In the exosphere, this is the outermost layer of the atmosphere. Is the exosphere. And this, like I said earlier, we can pretty much consider this space. Even though technically it's not, but it kind of acts like it. Here are a couple of diagrams kind of showing distances. We have the troposphere up to 12, or about 7.5 miles. Stratosphere up to about 21 miles. Mesosphere up to almost 50. Thermosphere up to pretty close to 200. Beyond that, the exosphere. And then the other one, you can see temperatures and pressure there as we go up. And it's actually, if the pressures look different, it's because it's in inches of mercury instead of psi. So it's how it's measured on a barometer. And then you see temperatures there as far, well, all the way off to the right side. So what you need to do now is go answer the science video question and fill that out.